Have you ever been working with data in Python and just sat there watching a for loop crawl along, thinking there has to be a better way? Well, you're in the right place. Today, we're going to pull back the curtain on the magic that makes NumPy so incredibly fast: vectorization and broadcasting. This will change the way you write code. So let's just start with this weird little puzzle. How on earth can one single line of code be massively faster than, say, 5 lines that do the exact same thing? It feels wrong, right? But the answer to this is one of the biggest secrets to writing high-performance Python. All right, first things first, we need to talk about our common enemy, the thing that slows us all down, the good old Python for loop. If you've ever dealt with a big data set, you know this pain. You know it all too well. Just look at this. On the left, you've got the classic for loop. Yeah, it works, but it's kind of clunky, takes up space. On the right, you have the NumPy way. One clean, beautiful line of code. Now, it obviously looks better, but that's not the point. The real story here is speed. That one line can be hundreds, sometimes thousands of times faster. No joke.
So what's the deal? Why are Python loops so slow? Well, it all comes down to the Python interpreter. Think of it like a micromanager. For every single item in your loop, it has to go, okay, what's this thing's type? Where is it in memory? Okay, call this function, one by one. It's like sending 1,000 separate postcards instead of one single email. All that overhead just grinds everything to a halt.
So how do we escape this micromanaging interpreter? How do we get that speed? Well, that brings us to our first huge concept, vectorization. This is NumPy's superpower. So what is it? At its core, it's pretty simple. Vectorization means you apply an operation to the entire array all at once instead of going through it piece by piece. You're not thinking about individual numbers anymore. You're thinking about the whole array as one single thing. And how does NumPy pull this off? Well, here's the secret. It's not really Python. When you do a vectorized operation, NumPy hands off the job to super fast, pre-compiled C code. Even cooler, it uses a trick your computer's processor can do called SIMD. That's single instruction, multiple data. That means your CPU gets one command, like multiply by 2, and bam, it applies that command to a whole chunk of your data at the exact same time. It's like parallel processing on a tiny scale, and it is crazy fast. Okay, so vectorization is a total game changer when your arrays are the same size. But what happens when they're not? What if you want to add a single number to a big array, or combine arrays with totally different shapes? Do we have to go back to those slow, ugly loops? Nope. And the answer is NumPy's other superpower, broadcasting. This is the incredibly elegant, almost magical way that NumPy handles operations between arrays that just don't seem to fit. So here's the key idea. Broadcasting works by conceptually stretching the smaller array to match the shape of the larger one. Now listen, that word conceptually is doing all the work here. NumPy is smart. It doesn't actually create copies in memory, which would be slow and wasteful. It just pretends to, which is why it stays so incredibly efficient. I know, conceptually stretching sounds a little bit like hand-wavy magic. So let's actually visualize it. Let's see what NumPy is really thinking. We're going to start with the simplest, most classic example you'll ever see. Just adding one number, a scalar, to every single element in an array. So in your code, you just write array plus 10. So simple, but here's what NumPy sees in its head. It takes that single number, 10, and it stretches it out to match the length of the array. Then it can do this simple element-by-element addition. And remember, this is a virtual stretch. That array of 10s never actually exists in memory. It's pure efficiency. All right, that's easy enough. But let's kick it up a notch. What about a trickier situation? What if we want to add a 1D array, just a single row, to a whole 2D array, like a table of data? This is where broadcasting really starts to shine. So look, we've got our 2D array with 2 rows. We want to add that smaller 1D array, 1, 2, 3 to it. Broadcasting just gets it. It sees that the shapes are compatible, and it conceptually duplicates that 1D array for every single row of the 2D array. Then it performs the addition, no loops required. You get exactly the result you want, and it happens in a flash. Now, this is not just some cool, abstract trick. This is something you use every single day in data science and machine learning. Let's look at a super practical, real-world example.
A super common task is data normalization. Say you have a data set, right? You need to scale all your different features so they're on a level playing field. A standard way to do this is to find the average of each column, and then subtract that average from every single value in that same column.
And this right here,
This is the payoff. If you were using loops, this would be a nested, clunky, and slow piece of code. But with broadcasting, it is one single, clean, beautiful line. NumPy automatically broadcasts your 1D mean array across all the rows of your 2D data array. It just works. It's fast, it's easy to read, and it's powerful.
So, let's wrap this up. What's the big idea here? It's simple. Stop thinking about individual numbers. Start thinking in whole arrays. Ditch those manual Python for loops for any numerical work. Use vectorization to get that massive speed up by going down to the C level. And when your array shapes don't match, just let broadcasting work its memory-saving magic. I promise you, your code is going to be cleaner, way faster, and honestly, a lot more fun to write. So the real goal here is to change the way you approach these kinds of problems. I'll leave you with a little piece of homework. Go look at some of your own projects. I want you to ask yourself, what slow, clunky loops do I have right now that I can completely eliminate with the power of vectorization and broadcasting? Go find them.